Okay, so in the previous chapter we have discussed Euclidean theorem and some propositions, and now we'll give you the main result of integers. And it's a very wonderful result, the fundamental theorem of arithmetic. And let's begin. So basically we have already seen in chapter 8, proposition 8.1. So in chapter 8, proposition 8.1, we said that every integer greater than 1 is equal to a product of prime numbers and it has a prime factorization. That is, every integer has a prime factorization. The main result of this theorem is fundamental theorem of arithmetic, and this tells us that this prime factorization is unique. So you can write here that is it has a prime factorization. The fundamental theorem of arithmetic tells us that this prime factorization is unique. In other words, there is essentially one way of writing an integer as a product of primes. Okay, and surprisingly, this theorem may not seem terribly thrilling to you at first sight. However, it is in fact one of the most important properties of integers and has many consequences. And we'll present some of the consequences in this chapter and give you a very nice understanding. So let's present the theorem. (11.1) Fundamental theorem of arithmetic. Okay, says that let n be an integer with n greater than or equal to 2, then number 1, then n is equal to a product of prime numbers and we have that n can be written as P1 dot dot Pk, where P1 up to Pk are primes and the condition that P1 is less than or equal to P2, P2 is less than or equal to up to so on P and sorry K. Okay, this is the first point. Second one, this prime factorization of n is unique. In other words, if n can be written as P1 dot dot Pk, and it can also be written as Q1 dot dot QL, and where these P1 up to Pk are simply, I should write Pi's and Qi's are all primes with the condition that P1 is less than or equal to P2 and it is less than or equal to just Pk, and these Q1 is less than or equal to Q2 less than or equal to QL. Then we have, because this prime factorization of n is unique, that means that we should have K is L is equals to L and all the Pi are equal to Qi for all I is 1 up to K. Perfect. So this is the theorem. It says that we have an integer n with the condition that it is greater than or equal to 2, then n can be written as a product of primes. It is greater than or equal to 2 because the first prime we have is 2. So that's why. And then this prime factorization is unique. So if you can write up an integer in the product of primes, then there will not be any other prime factorization. And if there is, then both prime factorizations are similar or equal. And this is the theorem. We'll now prove it. And to prove it, we say that why we want to say that all these primes are less than or equal to each other, because this condition determines the order in which we write down the primes in the factorization of n. So let me give you an example and then we will prove it. So a small example for why we write this and this, or this condition. So that example says, so let's say we have 28 can be written as product of 2 cross 7 cross 2, 7 cross 2 cross 2, and it can also be written as 2 cross 2 cross 7. But if we specify that the prime factors have to increase or stay the same, then the only factorization is that 28 can be written as 2 cross 2 cross 7. And this is the only factorization by this condition. Okay? Let's prove this theorem. So proof. Now we will prove part 1 in just proposition 8.1. So if you just go to the chapter 8, you will find this proposition. Now, so part 1 is just proposition 8.1. We have already done that in chapter 8. So you just have to go there and then see how a integer n greater than or equal to 2 can be written as a product of primes. Okay. Now, for the uniqueness part 2, for the uniqueness of this prime factorization, which is part 2, we prove this by contradiction. So suppose there is some integer n which has two different prime factorizations, which has two different prime factorizations. Say that n is product of P1 up to Pk, and they are also equal to Q1 up to QL. Okay, where P1 is less than or equal to P2 and so on. And also Q1 is less than or equal to Q2 and so on to QL. And the list of primes, the list of primes P1 to Pk is not the same list is Q1 to QL, because we are proving it by the contradiction. So we are assuming that n can be written as product of n can and have a different prime factorization, two different prime factorizations, and then these primes are not equal. Okay. Then what can we say about this? So now in the equation, this equation, equation 1, that P1 dot dot Pk are equal to Q1 dot dot QL. What we do, cancel any primes. Primes that are common on both sides. Okay. Since we are assuming the two factorizations are different, so since we are assuming the two relations are different, not all the primes cancel. In the cancelling step, okay, and we end up with an equation that R1 dot dot RA is equal to S1 dot dot SB. Okay, and where each Ri belong to the set P1 up to Pk, comma, each Si belong to the set Q1 up to Ql. And none of the Ri's is equal to any of the Si's. And none of the Ri's are equal to any of the SIs. Okay, so basically we are saying this, that Ri is not equal to Sj for all I, comma j. Perfect. That means now we obtain a contradiction. So after this, we obtain a contradiction. Now we obtain a contradiction which is certainly R1 divides R1 dot dot RA. Hence, R1 divides S1 dot dot SP by, okay, hence, so by proposition 10.6, this implies that R1 divides all of the SJs, divides some of the SJs for some J. However, the SJs are primes. Sj is prime. So it's only divisors are 1 and Sj itself, and hence R1 is Sj. But we know that none of the Ri's is equal to any of the Si's. So this is a contradiction. And this completes the theorem, the proof. Okay. So part 1 we have shown by, we have already proved in proposition 8.1. If you want to see, I can show you that. Chapter 8. So chapter 8 says is the induction, and then proposition 8.1, you can find it here. Okay. Prime factorization, and here we have this position 8.1. So every positive integer greater than 1 is equal to a product of prime integers. So this is what we have. Okay. Go back to our chapter 11. So we have proved the theorem. Now, of course, in the prime factorization given in part 1 of theorem 11.1, some of the PIs may be equal to each other. And if we collect these up, we obtain a unique prime factorization of the form. So by part 1, so this is a consequence or like other way of writing it. So by part 1 of theorem 11.1, some of the PIs may be equal to each other. If we collect these up, we obtain a unique prime factorization of the form. And that form is that n can be written as product of p1 power a1, p2 power a2, so on up to pm power m, where p1 is less than p2 is less than up to pm. Now they are not equal in this prime factorization. And the AIs are positive integers. Okay. So this is also a very nice consequence, or like the other way of writing the thing in part 1. Okay. Now we will write some consequences of the fundamental theorem. So let's give the topic some consequences of the fundamental theorem of arithmetic. Okay. And so first, there is an application of the fundamental theorem of arithmetic that looks rather more obvious than it really is. That application is proposition. So we write it by proposition 11.1, in which we say that let n has a prime factorization, which we have given here. So where the i's are primes with the condition that p1 is less than p2 and it is less than so on, and the ai's belong to the positive integers, or if m divides n, and then m can also be written as a prime factorization of primes, and this is very interesting. With these bi's are greater than or equal to between 0 and ai's for all I. And to give the understanding, we can say an example. It says that the only divisors of 2 power 100 into 3 square are the numbers 2 power a and 3 power b, where 0 is less than or equal to a and a is less than or equal to 100, and 0 is less than or equal to b and b is less than or equal to 2. So if you know the prime factorizations, and then if you know the powers of primes, then you can say then you can talk about the divisors of the number from this prime factorization. So let's prove this. Let's give the proof. So we are saying if m divides n, then m can be written, or n can be written as m into c for some c an integer. Now let m can be written as a prime factorization of the primes, comma c can be written as the product of different. C also have the prime factorization, so then n is m into c gives the equation you just multiply these prime factorizations. So you can write that because m could have been written as n could have been written as the product of these primes, or we have already mentioned that here in the proposition statement. So n has this prime factorization, and this prime factorization is equal to product of these two prime factorizations of m and c, right? And this shows that by fundamental theorem of arithmetic, (11.1), the primes and the powers to which they occur must be identical on both sides. Hence, each qi is equal to some pj, and its power ci is at most aj. And this proves the proposition. This proves the proposition. Perfect. Now, we can use this to prove some further obvious looking facts about integers. And for that, we can define the least common multiple of two integers a and b and denote it by this. So let's say define the least common multiple of two integers a comma b and denoted by LCM of a comma b, and this is to be the smallest integer that is divisible by both a and b. Okay. For example, we say that LCM of 15 comma 21 is going to be 105, right? Okay. Now, by this, we can give another proposition. And that is 11.2, which says that we have a comma b greater than or equal to 2, the integers with prime factorization, that a can be written as p1 power r1, p2 power r2 dot dot pm power rm, and b can be written as p1 power s1, p2 power s2 to pm power sm, where the I are different distant primes, and all Ri comma Si are greater than or equal to 0, but so yeah, we allow sum of Ri and Si to be 0. Then we have following consequences. So one, the HCF, highest common divisor of common factor of a comma b, is nothing but p1 minimum between r1 comma s1 dot dot pm minimum between rm comma sm. Right. Number two, LCM of a comma b is p1 power maximum between r1 comma s1 dot dot pm power maximum between rm comma sm. Right. And the connection between LCM and HCF is that LCM of a comma b is nothing but the product of a b divided by the HCF of a comma b. This is the consequence. So how easy it is. Right. Now here is our next application of fundamental theorem of arithmetic. And we say proposition 11.3 says that let n be a positive integer, then the square root of n is rational if and only if and only if n is a perfect square. That we are saying that n should be equal to some m square for m to be an integer. Okay, right. Now, a similar argument applies to the rationality of cube roots and more generally nth roots. In the statement, we say a positive integer is a square or the nth power. We mean that it is the square of an integer or the nth power an integer. Okay, perfect. Now we'll give the similar kind of proposition for the nth power. Okay, so proposition 11.4 says let a and b be positive integers that are co-prime to each other. So that is let a comma b are positive integers that belongs to z plus, and HCF of a comma b is 1, or a and b are or a and b are co-prime to each other. Okay, then a, if product of ab is a square, then both a and b are also square. So this is to say that if AB is some m square for m to be an integer, then A is some s square, comma b is some r square for s comma r to be an integers. Okay, perfect. And this, if we generalize, so more generally, if the product of AB is an nth power for n to be positive integer, then both A and B are also nth powers. Now, by means of, so we can say that AB is a third power for some third power, then A and B are also the third powers. So they are equal to the third power of some number. Okay. And these are all the consequences of the fundamental theorem of arithmetic. Right. Now we will give a very famous and very nice example. Okay, and then we will end the chapter. So the example is or the question is very innocent one. Can a let's write it with a different pen. So can a non-zero even square exceed a cube by 1? Exceed a cube by 1? This is the question. Now, the non-zero even square are, of course, the integers. So you can write the non-zero even squares are 4, 16, 64, 100, 144, and the cubes are and so on, and the cubes are, they can be negative, -8, -1, -1, 0, 1, 8, 27, and so on. Perfect. In other words, we are asking whether the question, the equation, in other words, we are asking whether the equation, which equation? The equation 4x square is y cube plus 1. And this is 11.1 equation. Has any solution? With x comma y, both non-zero integers. Perfect. So what we have done? So we have asked a question which is an example of a Diophantine equation. So if you search that, I'll explain the Diophantine equation. This is an example of Diophantine equation. Okay. So in general, a Diophantine equation is an equation for which the solutions are required to be integers. So Diophantine equation is an equation for which the solutions are required to be integers. Okay. Most Diophantine equations are very hard or impossible to solve. Okay. So you can also add most Diophantine equations are very hard or impossible to solve. For instance, the equation x square is y cube plus k has not been completely solved for all the values of k. Has not been completely solved for all values of k. Okay. However, we have chosen a nice example. The equation 11.1 can be solved fairly easily. You will see, but the solution is not totally trivial and involves uses of consequence 11.4. Okay, fundamental theorem 11.1. So let us go about solving equation 11.1. So now we are solving this part. Okay. So solution. So first we rewrite it is that y cube is 4x square minus 1. And then cleverly factorize the right hand side to get. And then you can also get 2x plus 1, 2x minus 1. So you can get y cube can be written as like this. Now the factors 2x plus 1 and 2x minus 1 are both odd integers. So you can say 2x plus 1 and 2x minus 1 are both odd integers, right? And their highest common factor divides their difference, which is 2. So the HCF of 2x plus 1 comma 2x minus 1 is 1. The highest common factor divides their difference. So their difference is 2x plus 1 minus 2x plus 1. And then we will cancel out these, and this is 2. So the highest common factor of these two is 2. So divides their difference. So not equal to, but divides their difference, okay? Which is 2. Hence, their HCF is going to be 1. Thus, which means 2x plus 1 and 2x minus 1 are co-prime to each other. Okay. And their product is y cube, a cube. Now, by having this, by proposition 11.4b, follows that because we have said that if the product is a cube, then AB should be the cubes also. So it follows that 2x plus 1 and 2x minus 1 are themselves both cubes. However, from the list of cubes, it is apparent that the only two cubes that differ by 2 are 1 and minus 1. So you can write that, however, from the list of cubes, that is -8, -1, 0, 1, 0, sorry, 1, 8, 27, and so on, it is apparent that the only two cubes that differ by 2 are -1 and 1. Therefore, x must be 0. And we have shown that the only even square that exceeds a cube by 1 is 0. Only in other words, there are no non-zero such squares. So this is the end of the chapter 11. Perfect. So we have just solved one of the Diophantine equation. See you in the next lecture.